All right, welcome to the first video on the CCI BattleDrones competition. My name is Kevin Schrader, and I'm going to walk you through some of the software that we've put together for each of the teams to use as a kicking off point. So if you're not familiar with the BattleDrones goal and competition, this is going to be kind of our first inaugural competition. Hopefully we do this every year and build on it in complexity. But the goal of this is to get students engaged with autonomous vehicles and big data, neural nets, and start them off coding at a young age. So hopefully, if you're one of the students that's watching this video will be helpful and insightful. I plan on doing a whole series of these so that you can kind of see me go through the code that I wrote and how it's supposed to work and how you can engage with it. So that you feel comfortable enough with it that you can add to it, make it your own, make it unique. And that's the purpose of this competition. So welcome. Hopefully this is good, and feel free to reach out to me if you guys have any questions. But today we're talking about the Matlab simulator that we kicked off for this. This code that lives in Matlab is something that I built kind of over the last couple of months. And there's going to be, as close as we can, a one-to-one translation of the code over to Python, and that's what's actually going to be flying on the drones. So you can see one of the versions of the drones, we've actually updated the body of this drone, so it'll look a little bit different when you assemble your own, but the software is what's critical. Okay, so let's walk through the big picture of what this drone can do when it's fully operational. So here at the front, we've got a camera, and so the camera is going to be the primary sensor of the drone. And I say primary sensor because it does have some other ones on it, but they're not ones that you as the programmer or developer are really expected to interact with. Okay, so the camera is going to be providing computer vision, and then that image is going to be sent here in the back. You can actually see our Jetson Nano. So Jetson Nano is a single board computer that's got a rather large GPU for its size. And so it's able to run computer vision algorithms like a neural net to do classification. So we have trained a neural net. There will be a whole separate video series on how to build up your own neural net with the training data that we are going to provide, and then show you how to make your own additional training data. That data is all about identifying the gates that the drone needs to fly through. And so you take a picture, you send it to the neural net, it will find in that picture where all those gates are and identify the corners. So find each of those corners of the gate on the image. So you get these pixel values on that image. And those pixel values, if you undistort your image or you use not a wide field of view and camera lens, then you can roughly connect those pixel locations to angular locations off of the pointing of your drone. So if your drone's pointing in one direction, you can measure based on the pixel location degrees across the horizontal plane. We'll call that our pan angle, and then degrees up from that horizontal, which we'll call our tilt. So you get pan and tilts for every corner that's in the frame. Okay, and from there, we're going to use a lot of geometry, a couple of fancy algorithms to take that and get your drone to be able to move through the gate and go through the whole obstacle course. So that's our objective. We're giving this to you guys January or end of December 2021, start of January 2022. And then soon after this, we will provide the kits to each team that's signed up. And the actual competition ground. So Virginia Tech has let's pull it up, has its own drone park. So you've got a rather large space. We'll put up the drone gates in the space and give you guys the map, and you'll be able to fly through it with your own self-built drones. Okay, so that's going to be the goal. Today we're going to just dive into the Matlab. The goal of this is so that you can get a little bit of experience with the code that's running the autonomy. So these are autonomous drones that need to fly through the course. That means no remote control. You don't get to fly it yourself. the computer is going to do it, and you're going to build the computer. So that's our goal. And this first year, we're going to keep things slow, low frame rates on the computer vision, low speeds on the drones, just to go through the motions. Each year, we're going to add complexity, add speed, add different types of obstacles until we get a truly challenging autonomous system that can handle a rather robust environment. So let's dive in to what we have. So here is the code that we have. It kind of comes in a large area. On a separate video, I'll show you how to download this off of a Git repo, which is where we'll post it for everyone to use. But we have a number of different folders with different types of commands in there. And today I'm going to walk you through kind of the logic of the core structure. What's underneath, what's the bare bones? And then in subsequent videos, I might pull out a specific function that I find interesting and walk you through the mechanics of what it's going through. But for now, we're just going to kind of walk away from what the code is at its core, or sorry, at its face value, and dive down into what's happening underneath. And so for that, let me pull this up. So here's a simple little script that I have. And it uses these two functions, Buildgate and plotGate. So nothing fancy is happening here. I'll just give you an example of it. So let me clear this all off. And talk about this. The first thing that's important is make sure that all of these subfolders are in your Active Directory. So you can run a command like this. I'm just adding things into my path. So all of the subfolders inside each of these and all the scripts in there are available. And then these are just some generic, simple parameters I'm going to put into my workspace. So they'll show up down here. And that's as far as I'm going to go here. Okay, so let's talk about this. Here's our Buildgate command. And this is one of the core ones. Buildgate, it's not going to do anything too fancy. When I run it, it gives me positions of all the corners of the gate. Okay, so let's go ahead and open up Buildgate. And you can see it. There's a fair amount of documentation, so you can understand what's going on. But this is all it is. We're going to place corners on a unit. So we're just 0, 0, 0, 0, 1, 1, 0, 1, and 1. So these are, if you're following that around in 3D space, it's just 4 points of a corner. We're going to multiply it by the size of our gate. The gates that we're going to be building are about 3 feet on an edge. That's the inner opening. So roughly, let's put that at 1 meter. And then I'm just going to shift it around so that the gate center is at the origin. That's all I'm going to do. And that's this whole command. All it does is it returns out my corners. So we can go ahead and save that. We'll run that. And now corners is added to my workspace down here. The next thing that I'm going to do is just a plotting script. So this is plotGate, and there's a simple version. There's also a detailed version that you could kind of dive into if you wanted to actually add in some sort of texture to it and give it a prettier look. You could use that, but for now, we're just going to do a simple line plot. So here's corners, or sorry, plotGate, and it's just going to take those corners that we have, and functionally, all we're going to do is use the line plot command. So line, and then we list out our X position of our corners, our Y, and our Z. And that's it. All right, I've set in some parameters of how they should look. And if you want to give it a label, you can go ahead and name that, and it will actually show up on the plot. So if you want to name it, gate number 1, you could, but that's an optional parameter. So here you go. So let's dive back in, and we'll go ahead and plot our corners. And this is going to give us a nice 3D plot. And hopefully, if you're familiar with Matlab, you're used to this. So here's a plot. It looks two-dimensional, but if we look at it from the right orientation, you can see those 4 corners. Okay, so let me do a little bit of editing. Let's dock this guy over here so we can see it. And we will move me over to the other side. All right, and let's do just a bit of formatting. There you go. Okay, so here it is. And in Matlab, the Matlab figures are really one of the best parts of Matlab, in my personal opinion. And that's why we didn't just dive into a code like Python. You can do a lot with figures in Python, but it's just really nice to use the functionality of the figures in Matlab. And actually, the rest of this little recording is about how we're going to reference these figures to generate a first-person view simulator of the drone. And it really comes down to the fact that when I click on this figure, I can move where this camera is around, or where it's looking, just on where I'm clicking. And there's a lot of those things that you can actually do by clicking on the figure and moving it around, but you can also set it in your code. So if we come back over here, we've got a couple commands like this. So set command is just a generic MATLAB command to set a parameter, and I'm going to give it an option that I want to set. Object that I would like to set. GCA, that's another MATLAB thing. You may not have ever used it, but it just says get current axes. So this figure that I've clicked on is my current axes. And so if I typed in GCA and ran it, it's actually going to return the axis that is this figure. This figure lives in this axis, and here's all the parameters that are there, and there's more properties that I can do. So let me go ahead and run these. I'm going to place the camera at a very specific location at 10 feet, or sorry, the camera's target. So where is it looking? I'm going to put it at +10 in the Y direction. And when I do that, you shouldn't really see anything too interesting. The visualization moves around. I'm going to go ahead and run where the camera's current location is. So I'm going to move it back -15, also on that Y-axis. And so now we're looking right at this gate, and I can set things like the field of view of it. And that changes kind of my field of view, how wide I can see relative to everything. So there are some simple parameters. And as we play with these and we realize that those are things that we can automatically manipulate, we can set something up like a for loop that's going to progressively move us from one camera location to the next. And that's going to make it feel like we're moving along a trajectory. So I've set up a for loop. My stepper variable is just called move forward. And I'm going to run this set get current axis camera position, and I'm just going to move it across in the Y direction. Okay? And after each time I move it, I'm going to pause for a little bit so it's not all happening instantaneously. So let's just run this for loop and watch what happens to my figure on the right side. Here it goes. I move forward. It's hard to tell what happened. It looks like it disappeared. We actually made it all the way through that gate. Notice that the gate was at 0 in the Y direction when we built it, and we went from -15 to 5. So we went through it. It's hard to tell that we went through it because there's no background. There's nothing else going on. So to make this a little bit more involved, let's go ahead and add some extra stuff to it. So we're going to go ahead and clear everything off, close everything down. And these are some parameters that I want to keep track of. They're not critical at the moment. We'll talk about them in the future. But I'm just going to set some of these. This is the add path command that we've already activated. That pause timer that I set up for visualization, this we're going to just make a global variable so I can access it in any workspace that I jump to. So any script that I run or function that I run has access to pause time. Same thing on the dimension of my gate. I found that this was something I just wanted to have access all over the code. So I went ahead and put it in. And then all I'm going to do is set my parameters. Where do I want my camera to be located initially? So I put a flight altitude. It's about half of the side length, but I want to make sure I'm up off the ground. I don't want to be right at 0. I'm going to put a ground layer in at 0 in the Z direction. And here's where I'm going to start. I'm going to start 25 in the X and -20. And I'm going to, my starting direction, the direction that my camera is facing, is just going to be forward. So let me take a second to talk. Why is Y forward? The coordinate system that I've built is a right forward up system. So if you're familiar with the right-handed rule, if you can get all your fingers out and set everything up so that sorry, not a right forward, it's a left forward up system because forward is my middle finger. So Y direction is forward, and that's just always going to be the case. In Y is forward, up is always going to be 0, and to the right is my positive, to the left is my negative. Okay, and so when I start off at positive 25, I'm going to kind of start over to the right of the origin. So let's just put all these things in our working space. And this command, it's a function, and all it's going to do is it's going to try to build my rendition of the Virginia Tech drone cage in a Matlab figure. So if I run this, you'll see that figure pop up. And there it is. This is my figure, and I can come in and I can look at it from all around. And let's go ahead and dock this guy. Okay, so there it is. This command references that more detailed gate design. So you'll see the gates look slightly different, but they're using the exact same command. And then we have a build drone. Now, this one might be worth opening up. And what you can see is inside the build drone are all those same set commands that we were doing before. They're just going to go through, put in the camera, put it in a specific location, make sure it's pointing the right direction, and work from there. One thing that I think is important is the target. If you remember, we had a set camera target. It was a point in 3D space, and that was set up so that you could put a point and move your camera around it and stay focused on that interesting point. But that's not how drones work. Really, if we're moving them around, they're going to stay in the same orientation that they always are. So here, I make the target just a little bit in front of where it's currently looking. So I put in a look vector, which is 1 unit in the forward direction, and I just add that to the gate's current location. So anytime that I move the drone, I'm also going to move where it's looking. And that way it just kind of stays looking forward, unless I tell it to look to the left or right. Okay, so let's go and run this command. So build drone, the first parameter is its starting location. The second is where is it looking, and then the last one is its field of view. Okay, so we're going to run that. Evaluate section. Okay, now let's talk about what I've done here. So in this command, I have put in just a little bit of random noise. When you actually are flying the drone around in the drone cage, even if it's autonomous or you've got a remote control, when you set it down and you tell it to take off, it's not going to be precisely where you want it to be. There's always going to be a little bit of error. And if you tell it to move forward a few feet, it's going to do that, but there's going to be disturbances and inaccuracies in the controllers that are going to cause it to not be precision exactly where you want it. It's going to have a little bit of error. So when I make my starting location, I'm going to add a little bit of noise. And then I'm going to save my starting location as where I think that drone is, the estimated drone location. And I also have an estimated drone heading. Which way is it facing? So both of those are going to have just a little bit of noise on them. To get the error in the direction it's heading, you can't just add a little bit of noise. You have to rotate a vector just a little bit. So if you're not familiar with rotation matrices, we'll have a video series on rotation matrices. But just understand it's a matrix, so it's just a little linear algebra trick that we use to take a vector and turn it just a little bit without making it grow in length. So they're relatively straightforward. If you don't understand them, we'll make a series for you on those. But that's something you would pick up in a linear algebra class. So we've built our drone, and we have estimated where that drone is. So here we're looking at our course. Everything is right there. And let's start playing around with it. So I can run a command like this, let's try that again, turn drone, and using our right-hand rule, turning towards the left is actually going to be a positive rotation with the right-hand rule. Turning to the right in a clockwise fashion would be negative. So I see this gate over here, it's on the right side, so let's put in a negative 10-degree turn. And there it goes, it walks through that motion. Let's go ahead and slow down my visualization a bit so that as we walk through it, it's not quite as fast. So we'll change our pause time. That's how fast the frame rates update. And let's just do that again. Let's turn -5 degrees. There you go. You can see it a little bit choppier. And we want to do this until the drone roughly, or the drone gate is roughly dead center. So we're going to just keep turning. Okay, that looks pretty good. And now let's give it a move drone command. Move drone. Let's move it forward 5 meters. There we go. We're doing that. Let's do that again. That looks still pretty dead center. And we just made it through our first gate. And so we can just keep putting these in, moving it piecewise by piecewise. Occasionally we can come in with a turn drone. Turn drone. And this one needs to be a positive rotation because we're going to go counterclockwise. Let's do that again. Again. There we go. That looks about right. And now we can do another move drone. There we go. All right, we're through. Now, you might not know where the next gate is. Each one of these was labeled. In the kind of flyer, there is a general path, but it doesn't have a lot of details. When you guys actually come to building your own autonomous system, we will give you the map. This is where, honest to goodness, all the gates will actually be. And so you'll have gate 1, gate 2, gate 3 comes up here, then you're back down here for 4, 5, 6, 7, 8, 9, 10, and you're done. You got to get through all 10 gates. You'll have the map, but what you won't have is GPS. You'll know where the gates are located in your field, but you won't actually know where your drone is located. And so what we need to do is we actually need to use that computer vision, figure out where all the corners of gates are, and then use that information with our big brains in geometry to back out a really good estimate of where our drone is relative to each of those gates. And once we know that, we can place our drone on the map and give it the right commands to move it forward. If your drone ever gets lost, each gate is equipped with QR codes. Each corner has a QR code that you can go up, inspect that QR code, get a reading, and it will tell you this is the gate you're at and this is the corner of that gate. So you will know where you are in 3D space anytime you need that. But here's the catch. That's going to take time. It's going to slow you down. And this is a drone racing competition. First one to get to the end wins. The speed is the key. In each one of these, as you go through gate by gate by gate, it's going to take time. If you miss a gate, there's a time penalty. If you miss 2 gates, it gets really, really steep. If you have to turn your drone off or take over manual control, there's going to be a rather stiff time penalty on each of these. Whoever gets the best time score is the winner. Okay, so your goal is going to be to take what we've given you in terms of this code and try to optimize it, make it better, make it faster, make it more aggressive. Anything that you can do from the software side of things is fair game to give you a competitive edge. So with that, let me do one last thing. Let's run the main driver script. This is our simulator. And here is the baseline autonomy. We'll dive into each of these functions on another video. But the first thing that we're going to do is we're going to find a specific gate that we want. We're going to approach that gate, and then we're going to fly through that gate. We put that on a loop, and we just iterate gate after gate until we get to the end. The problem is it's autonomous. And so sometimes when it updates its location based off the geometry that we've given it, it might do it wrong, and it might end up getting lost. So there's nothing in here yet to help it figure out when it does get lost, if it goes through. So let's roll our dice, take in these random number generators, and see if we get a lucky run. So let me click run, and you'll see this whole thing play through. And immediately broke. That was not lucky. Okay, there it goes. It kind of had a flub on gate 1. It fought its way through, and there it goes. Going each gate by each gate. It looks like it missed one, and there you go. So there was our whole course. That was everything that we told it to do. And what you'll notice is it wholeheartedly missed gate 1, corrected, got to gate 2, moved forward, came around through 3, got to 4, kind of tried to realign, made it through 4, made it through 5. It missed 6 entirely. Made it on to 7, 8, 9, and 10. Okay. In the end, if we come over here, based on the visualization speed, which is kind of made up, I'll give you, but it took 20 seconds to do all of that. The way that we are scoring this, it missed gate number 1, that's a 5-second penalty. Okay, so take your 20 seconds, add 5 to it. Did well all the way through, it missed gate 6. So we are going to add 5 squared to this. So it gets 25-second penalties. That just doubled its time. So you get all the way through, and this one gets a score of 50 seconds. Okay, that's the drone racing competition. Your job is to take what we've given you here over the next couple of weeks and months, see if you can make this better. What can you do that makes it more robust, stronger, faster, or just more aggressive? In the end, the way we're going to run the competition, when you come to the drone park in April and you race it, you get 3 tries. And we're going to take the best 2 of those tries. So maybe it's strategic to have an aggressive run that's a little bit more risky. If that pans out, great. If it doesn't pan out, no worries, we drop our lowest score. So with that, let me wrap up this video, and I will look forward to seeing you guys in the next one. Have a good one.